Okay, so we said that to induce current we need a change in magnetic field, but actually things are a little bit more elaborated than that. We induce current by changing what we call magnetic flux. Okay, and I have to define to you now what it is that we call magnetic flux. The magnetic flux depends on the magnetic field, but not only on that. Okay, okay, so we are going to use this letter, this Greek letter phi, to denote our magnetic flux. And before I tell you what this magnetic flux is this equation here, let me discuss this drawing here. So here we have a square, okay, so we have a wire. So this is a wire, just as before we had a circle. No, our loop was a circle. Here now we have a square. And the area within this wire, the area is the size multiplied by the size, no, L square, as you see here. Okay, the thing that we call flux depends on this area. Depends also on the magnetic field, but the magnetic field that goes through this loop, through this area. Okay, so you see here the drawing, the magnetic flux going through the wire. Okay, so let me write here this magnetic flux depends on the magnetic field that is passing, that is cutting this cross section, and that is cutting this um, area inside the loop. Okay, so let me put it here, our magnetic field. Okay, depends on the area. Okay, depends on the area of this loop, and depends on one more thing, which is the cosine of the angle between the direction of the magnetic field and this direction, which is perpendicular to the area. Okay, so I have here this direction that is perpendicular to the area of the loop. This direction forms an angle that we are calling theta. Form this angle theta with the direction of the magnetic field. So the thing that we call magnetic flux is the magnetic field, the area, and the cosine of that angle. Again, I repeat, what is that angle? That angle is the angle forming between the direction of the magnetic field that is cutting, that is crossing, that is going through the area of this wire, and the direction that is perpendicular to this area. Okay? What is the unit that we are going to use? Well, we saw before that in the international system, the unit for magnetic field is Tesla. The unit for area is meter square. This combination of Tesla and meter square receives a name, and it's Weber. Okay, so that's what you're seeing here, Weber. In the international system, that's the unit for magnetic flux. Okay, now coming back to the story of the angle. What is the angle telling us? What is the best scenario? When are we going to have the largest magnetic flux? When the magnetic field crosses this area perpendicularly. Okay, so when it comes in this direction perpendicular to the area. And what is the worst scenario? When the magnetic field is going to be when the flux is going to be minimum. It's going to be minimum if we come in this direction. So let me repeat what I just said. No, so this is a consequence of the dependence of the flux on the angle. If, so what is the maximum flux that we can have? Well, the maximum flux will be the one that we have when the magnetic field crosses this area perpendicularly to it. Okay? What is the worst scenario? The minimum magnetic flux that we can have. Well, the minimum is zero. The zero will be showing up when our magnetic field comes like this, parallel to the area. No? So parallel to the area means that our angle, no? our angle theta is going to be 90 degrees. So, and cosine of 90 degrees we know is 0. Okay? All right, so based on that, let's solve this problem. So this problem is going to be a repetition of what I just said, but now with numbers. We have here a square loop. Okay, so we have our square loop. The side is 10 centimeters, very well. So the area is going to be 0.1 multiplied by 0.1. So the area is going to be 0.01 meters square. What we have is a magnetic field of 1.24 Tesla. Okay, now these are the numbers. The question is, what is the maximum and the minimum values of the flux? Maximum, as we said before, maximum is when the magnetic field comes perpendicular. So maximum flux, magnetic flux, is when it comes perpendicular. So when it comes perpendicular, the angle is 0. So I know it's a bit strange. Perpendicular, the angle is 0, because remember this angle is defined like this. Is the angle between the direction of the field and the perpendicular direction. So if the field is already perpendicular, this angle is 0. Okay, so maximum flux happens when the angle is 0, which means when we write the equation for the magnetic flux, we are just going to use the field and the area, because cosine of 0 is 1. And this will then give us this 0.01 multiplied by 1.25 will give us 0.0125 Weber. Okay. When is it going to be minimum? Well, minimum magnetic flux is 0. When does it happen? Again, I repeat, when our magnetic field comes parallel to this loop. Parallel to the loop means angle 90 degrees. So theta here is 90 degrees, and cosine of 90 degrees is 0. So that's why the minimum magnetic flux is 0.